Okay, and last but not least, we're going to close out our function review with a little bit of exponential, logarithm, and graphing. So just to remind you about exponential functions, those are functions where we're raising a constant to a power. That constant is greater than 0, and actually that constant is not 1, because if it's 1, it doesn't act like all the others. So if your base, that b, is in fact bigger than 1, then you have a shape like these graphs here. And basically what happens is they grow very quickly. If you're raising 3 to a power, that's going to get big real fast. And then, of course, if you're raising it to a negative power, it gets closer and closer to 0, but it can never actually equal 0. So, of course, you could shift it up and down a little bit, as in this second picture. And the difference is if that base here is less than 1, but still positive, or possibly if your exponent already has a negative inside it, which is what I have in this example, the pattern shifts. So then now something like 1/2, as you raise it to a higher power, is going to get closer to 0, whereas if you raise it to a negative power, it's going to get really big. So just knowing that general pattern of how those graphs behave is an important piece. And then thinking about domain. Is there anything that you cannot plug in to y equals b to the x? Is there any number that cannot be an exponent? No, there's no restriction. So the domain is all real numbers. And as long as you have just a basic y equals b to the x, the range will be all positives. Okay. Unless it's shifted or reflected or something like that. And you can never get a negative number out of raising a positive number to a power. And the difference when we get to exponentials is we're rewriting. So if you remember, the base stays the same. The exponent is on the other side of the equals. So these two things are equivalent to each other, which is what I have written right down here. And you could think of it by thinking that log base b of x is equal to the exponent that you need to raise b to get x as an answer. So for example, what exponent do I have to raise 10 to get 100? Or 8 to get 1/64th? Or b2 to get 1? Or b2 to get b? Okay. So some of these properties of logs that you've learned about in the past, they really just come from kind of looking at logarithms as exponents. Now, you probably remember that ln of e is just 1, but remember ln is log base e. So what power do I raise e to get e? 1. What power do I raise e to get e to the 8th? 8. So I know that you have this idea in your head that ln and e cancel each other out. And they do, in that sense that you're already looking at a base e. So same thing here, log base b. What do I raise b to get b to the x? It's just x. Okay. This is not intended to be something where we're introducing you to logs for the first time. We're kind of just doing a quick review of logs. And if you need more review, then you should ask me for some help, because I'm not trying to teach you these for the first time right now. And if it's something that is an area of weakness for you, you're going to want to make sure that you get some extra practice. Okay, so just reach out and ask. Now, log looks a little different. Log base 3 or anything where the b is greater than 1 is going to have this general shape. It's always growing, but at a very slow rate. Versus if the base is less than 1, then it has that reverse. It's always decreasing, but also at a very slow rate. And you'll notice in both cases, you cannot ever cross over the y-axis. It has an asymptote here and here. Okay. And so that is directly related to our domain. The domain of log functions is 0 to infinity. You can only plug positive numbers into logs because they're inverses of exponentials. But that will change if it's a log of something else, like a log of x minus 4, then your domain, you have to make that x minus 4 be positive and then solve. So basic idea is that you can only take the log of a positive number, but the range will flip to all reals since the domain of exponents is all reals. And then we have those properties of logs that you've seen before. Just remind you of those real quick. If you have the log of a product, that's the sum of the logs. If you have a log of a quotient, that's the difference of the logs. And this just comes from rules of exponents. What do you do when you are multiplying two things with the same base? You add the exponents. What do you do if you're dividing two things with the same base? You subtract the exponents. And if you are taking the log of something to a power, you can pull that power out front and multiply it by the log. So again, just a brief reminder about logarithms. If you need more than that, please reach out. Last but not least, we just want to touch briefly on graph translations. We've talked about a lot of different functions in these series of videos, just trying to remind you about some basics. And we want to fill in this table to remind you that you can move a graph based on how you've changed an equation. So for example, if you started with an equation and then you added a constant to it, that's going to move the graph which way? Hopefully you said up. Of course, if k was negative, then that would mean down, right? So up for k positive, down for k negative. Okay. I guess one other way you could have said that is move the graph, how about we say vertically, k units. And so the difference is if you are adding or subtracting inside with the x, then that moves it horizontally. The thing you also probably remember is the minus is built into this. So if it's something like f of x minus 2, then that's actually 2 to the right. And if it was plus 2, then that's 2 to the left. And the reason for that is because the minus is built into the formula. I don't know why. I didn't make the rule. I just follow it. Okay, so what happens if we multiply the whole entire equation by a negative? It's going to reflect. And that'll go across the x-axis, whereas putting the negative in front of the x is going to reflect across the y-axis. Multiplying by a constant out front is going to do a vertical stretch. And if you multiply by the constant inside, that's a horizontal. So again, these things are intended to just kind of put these ideas back on your radar, okay? But if you might need to spend some more time with them, especially as we move through some of the calculus and we start seeing some of these in action. So a couple of quick places for you to go ahead and try to graph these and state the domain and range. I'm going to have you press pause on the video and give these a shot, and then come back and you'll see the solutions. Okay, so we got a couple of quick ideas here. The 1 in front of the negative 2 to the x will move the whole graph up 1. but then the negative in front of the 2 to the x will reflect it across the x-axis. So I took that original graph that would look like this, I reflected it, but then I moved it up 1. So what it would have had a horizontal asymptote here on the x-axis, but now that will be on the y=1 line. And if we're graphing the second one, this +1 also moves it up 1. I guess that happened twice. And the x-1 moves it 1 to the right. Remember, the inside with the x goes the opposite direction you would think. So I took my original logarithm that would do this. It would have a vertical asymptote usually on the y-axis, but since it's 1 to the right, its new vertical asymptote will be at x=1. And I shifted it up 1. Usually it crosses at that 1, 0 point. So now it's going to be up here at that 1, 1, which is actually 2, 1 since we moved it to the right as well.